Looking at the car from behind, we've got a picture that looks kind of like this. Here's the car. The forces that are acting on it are the weight, which is straight down with a magnitude of mg, the normal force, which is straight up, which is F sub n, and the frictional force, which is toward the center of the circle, which in this diagram would then point toward the left. Because there are no other forces acting in the vertical direction, we know Fn minus mg must be 0 for the forces in the y direction, so we know the normal force is equal to mg. What is Fs? Well, let's imagine that the car is going at its fastest speed, so it's using as much friction as it possibly can get. If it were to go any faster, it would slide off the road. So let's imagine that it's maximizing the amount of friction that it needs. What's the maximum amount of friction it can get? Fs max. So let's imagine the frictional force is Fs max. And we know Fs max is mu times the normal force. So we must have some static friction between the car and the road. Let's imagine that we've got a coefficient of mu sub s, static friction between the car and the road. Fs max is then mu s times the normal force, which is mu s times mg. That is then acting as our centripetal force. So that must equal the centripetal force that is keeping the car on the road. And we know the centripetal force is mv squared over r. Which leaves us with the result, and what velocity is this? Let's assume this is the maximum velocity, so we'll call this v max. That's the maximum velocity the car can have and still stay on the road. So we have that mv max squared over r is equal to mu s mg. Mu s mg. Divide off an m from both sides, multiply by r, take the square root, and we have v max is equal to the square root of mu s r g. And this tells us the maximum speed that the car could have traveling around a circle of radius r where there is a coefficient of static friction between the car and the road of mu sub s. Now just notice, the bigger mu sub s, the more friction we have, the faster the car can go. The less friction there is, the slower the car has to go and stay on the road. So for a slippery day, maybe an icy road day, what happens? Mu s is less, v max has to be less. Let's actually stick some numbers in there and see what we get. Let's imagine our car is going around a curve with a radius of 50 meters. And on a nice dry day when there's lots of adhesion between the road and the tires, we've got a very large coefficient of static friction, let's say of 0.900. We have that V max is equal to the square root of mu s rg, so the square root of 0.900 times r, 50 meters, times 9.80 meters per second squared, square root. Notice we've got meters times meters, which is meters squared over seconds squared. Square root of that will give us meters per second, just the units we would expect for the velocity. Multiply that, we get 21.0 meters per second. But now, on a very icy day, where the road is very, very slippery, let's imagine the coefficient of static friction is much less, say 0.100. Sticking that in for Vmax, we have root 0.100 times 50 times 9.8. Take the square root, we get 7.00 meters per second. Notice the velocity is much, much less. What does that mean? On icy days or days where the road conditions are not as good, you have to slow down. You have to drive slower, or else you could easily go off the road. What would happen if you tried to drive faster than Vmax? There would not be enough centripetal force acting on you to be able to keep you going around the curve. The car would slide off the road. Very, very good. Excellent. Let's keep that in mind when you're driving around on snowy days. Now, let's think about how can roads actually be, how can driving conditions be improved? In other words, how can you actually increase the speed that a car can go around a curve? If you've ever noticed race cars or a race car track, how have you ever noticed that the road is arranged, so to speak? You might have noticed that the curve is actually banked. In other words, the road is not flat, but it's on an incline. Let's think about that. Why does that affect the speed that a car could go around the track? Let's imagine we now have a car going around a curve, but now the curve is inclined. It's banked. How does that affect the motion? Well, let's draw a free body diagram. Here we've got our bank, and let's imagine that it is banked at an angle of theta. In other words, the road is inclined at an angle of theta to the horizontal. Here's our car going around the incline. We're looking at it now from the back. What forces are acting on it? Well, there's the weight that's equal to mg, a normal force which is perpendicular to the incline, and then there could be some friction acting on it. But notice, we want a centripetal force acting on the car pointing toward the center of the circle. The normal force has a component toward the center of the circle. What if it's actually the normal force that is acting as the centripetal force? This is not a separate force. The centripetal force is not a separate force. It's one of the other forces, or parts of the other forces, acting on the object that is acting centripetally. The normal force has a component centripetally. Perhaps that would actually be enough to keep the car on the road going in a circle even without friction. So let's imagine there are no other forces, only the weight and the normal force. And we want that component of the weight, the component of the normal force to act as our centripetal force. Well, if the weight is straight down and the incline is at an angle of theta, then we know that the weight, if we were to decompose the weight like we had done before, we know that that would be theta. But rather than making our coordinates along the incline, because we know the acceleration of the car is going to be centripetally, in other words, in the horizontal direction, we'll define our x-axis centripetally, in other words, towards the center of the circle, because we have no vertical acceleration. So if that's theta, we know that that angle must be theta between the normal force and the vertical, and our forces in the y direction are then this vertical component of the normal force, which you can see is the side adjacent to theta, so that's going to be Fn cos theta, and the weight in the negative direction minus mg. And we know there's no acceleration vertically, so that must equal may, and ay is 0, so we know those must be equal to 0. Bringing the mg to the other side, divide by cos theta, we have that Fn is mg divided by cos theta. That's not the usual result that we have for an object on an incline. That's because we actually have an acceleration taking place. This is not the same kind of relationship between the forces that we usually do. So we have the normal force is mg over cos theta. What about the forces in the x direction? Well, the only force in the x direction is the x component of the normal force, which is the side opposite theta, which will be Fn sine theta. So we have the forces in the x direction are Fn sine theta. The normal force is mg over cos theta, so we have mg sine theta over cos theta, and sine over cos we know is tan, so that's mg tan theta. That is the x component of the normal force, and that is what we want to act as the centripetal force keeping the car on the road. So we will set that equal to our centripetal force, which is mv squared over r. Well, we can solve for v, divide off the m, multiply by r, and we have that v is equal to rg tan theta square root. let's remember, what does that mean? That means for a car going around a banked curve, in other words, going around a curve that is inclined to the horizontal, that car, if it's going at just the right speed, that speed being the square root of rg tan theta, where theta is the angle of incline of the road, that car can go around that curve and not need any friction at all. It can make it around that curve without having to rely on friction. So this could be a very, very icy road, and if the car is going at just the right speed, even if it's icy, that car will still go around that curve. Very, very good. Let's stick some numbers in here. Let's imagine that we are going around the same curve we were talking about before with a radius of 50 meters. But now our road is inclined at a small angle, let's say 10 degrees. What do we get? We get V is equal to root rg tan theta, root 50 meters times 9.8 times tan 10 degrees. Multiply that out, and what do we get? We get 9.30 meters per second. Actually, not a whole lot faster than on a very icy road, on a very icy flat road as we saw before. So the banking of the incline, unless it's a rather large angle, that means you really still can't go all that fast unless there is friction helping you go along the road. If you are going faster than this speed, that friction will actually be pushing you toward the center. If you go slower than that speed, your car would actually have a tendency to slide down the road. So in that case, the friction is actually pushing you back up the incline. So, very, very interesting result. If you are going at just the right speed around a banked curve, you don't need any friction. If you go faster than that, you'll need friction to push you into the curve, acting down the incline, so that part of that friction is actually acting centripetally. But if you're going slower than that speed, the tendency of your car would be to slide down the incline, so the friction is actually pushing you up the incline. Very, very interesting result. Let's take a look at one more example of a centripetal force.